All right, guys. How are you? So we're back. I think 5 of you came to this. This is what you missed. Well, not only the picture. I think we spent 2.5 hours around the space shuttle. This gentleman here, who's a UF graduate, knows a lot of stuff about the shuttle. He spent 18 years working on it. I see some faces that were there yesterday. I don't know how much you guys slept. I didn't much. Realized that this is spring break for the rest of Florida, and it took me 4 hours to come back this morning. I'm exhausted, so I'm going to go very slow because I may fall asleep in the middle of the lecture. That was terrible. We had to avoid 75. There was a line of probably 20 miles. I don't know what the heck happened, but it was a nightmare. Anyways, it was worth it. To get into the center, I've never seen the Kennedy Space Center so packed with people. There was a line to get in. But we basically spent all our time there by the Atlantis, and the launch was awesome. It was right on time in Titusville. We watched it. Has anyone watched it online? Maybe it was right around 11 p.m., 11:02 or something like that. Oh, here it is. You missed. Oh, how did it go?
It went terribly.
Oh, okay. You can leave then. You can go and cry. Anyways. If you're planning to go by yourself, avoid the spring break. That's my only recommendation. Do you have any questions about these? I know you want to talk about the test. Before I do so, a couple more things that I wanted to bring to your attention. I did forward this link to you, I believe. It came from that lady, Stephanie, I know at AGI. They do have a lot of openings. I don't know what happened. There was an internship link here. When I opened this page a few days ago, there was a summer internship one, but I cannot find it anymore. Maybe they selected people already, I don't know. But that's something you may want to double check, because if any of you, I know there's only one person with the master's certification at this point, but if more of you get to that point, you may actually start looking for jobs in a place like this. This is a place where people seem to enjoy what they do. They develop tools for STK, not only. But they do have summer internships, and just double check. They may come back. I don't know what happened. Maybe I'm opening the wrong link, but I'm pretty sure there was a position there. So if you're interested, oh, you guys are liking the page right now? That's cool. If you're interested, you can come see me, and I can connect you to this person who sent me the info. Okay. What else? What they launched yesterday night, by the way, was the Cygnus cargo for the International Space Station. I think it docked this morning, early this morning, so it should be connected now. Okay, let's talk about this test. Once again, I've heard both sides of the story. It was way too easy. It was terrible. I couldn't understand a single thing. I'm getting used to that, I guess. So, I think I mentioned out loud, at least twice or 3 times, do not do calculations. This was designed to avoid calculations, except, and I meant it, my job is not tricking you guys. If I tell you, think about what you're doing because you don't need calculations, that's what I mean. These are the only 2 questions where you really needed to use the solutions for the Hohmann transfer and the bielliptic, those formulas that were given in the book. I've been asked the question, do I need to start from the energy and do the whole development and get to the final answer? Well, those formulas come from that. So that's fine if you use them, they're there. Why would I allow you to have the book open? Right? So those were the only ones where you had to, plug in some numbers inside a formula. But let's start from the end here. Why not? So these are, okay, those really, I gave you the MATLAB file. Just run that. It's very simple. If you're doing so when we started talking about Hohmann, we started circle to circle, and then we said we generalized. The 2 shapes can be just ellipses. One is bigger than the other, of course. And if you're going from the inner one, which is not an ellipse, is a circle, the strategy that is the best, if you're going to a bigger ellipse, is to end your maneuver at the apogee of the outer ellipse. And that is explained in those 3 plots that we discussed. It's a consequence of those 3 plots. So the answer here was end at apogee. End of the story. That's what you needed to tell me. And then there are some questions that were there just to show you can visualize orbits in 3D, because that's the most that what we have done. So this one in particular, Sun-Synchronous Orbit. What did we say? It's an orbit where the plane of the orbit is always looking at the sun. And it's rotating in such a way, in space, in such a way that it's matching the angular velocity of the planet around the sun, right? So that if you're looking at the sun now, and the Earth is going around the sun, you keep looking at the sun with your plane. And that was rotation of the line of nodes through the RAN. I think there was an uncollected homework about that, or something I gave you. But anyways, if you go, I hope I can go back to this image. If you go back to the very beginning of chapter 4, right? I think it's 4, orbits in 3D, it's 4. And I keep passing the point. There was that very first image that shows you the ecliptic plane and the seasons. So I just want to show you that. That is really the explanation of why it's 90 degrees after a fourth of a year. I passed it, right?
Yeah, it's not the first.
Yeah, it's really the first image. Almost. Here it is. Okay, so I'm telling you that here, summer solstice, the RAN is 0 degrees, and I'll draw a sketch to explain what that is. So this orbit, somehow, we don't need to know why, but it's sun-synchronous. It's exploiting the J2 the way we'll demonstrate, that allows you to actually have this perturbation exploited so that you can rotate with the Earth. And basically, if you're here with the planet, if this was your orbit, the plane of the orbit, a summer solstice, then here it's facing the sun the same way, and at this point it's 90 degrees. Why is it 90 degrees? Because we did define the ECI coordinate system as x pointing like the Aries direction, the vernal equinox direction, so that's x. And it doesn't change as your planet goes around. It's always pointing in that direction. Then let's just simplify and say that z is pointing at us. We know that there is a 23 degrees away from being normal to the ecliptic plane, but it doesn't really matter for this solution. And then y, as a consequence, will have to be this way. Now, the RAN is the intersection of the xy plane and the orbital plane. So if your orbital plane is like this, the RAN is measured as this angle right here, right? So what I told you is that at summer solstice, this angle is 0. So you are right on the x-axis with the plane. I don't care about the orbital parameters. That's all I'm asking you, the RAN. And if this plane has to continuously face at the sun, in this case it's starting at 90 degrees with the sun, then it will have to be at 90 degrees up here. Does it make sense? And it will keep going so that it's always looking at the sun, facing the sun. That's what sun-synchronous means. Is this clear? Is this 3D visualization of what's going on? Actually collapse into the plane, because that we're really talking about just one angle. Okay, that is that question. Let's see. Okay, this is something I wanted to reiterate about energy, just so that this time wasn't confusing. If you are on a hyperbolic orbit, your mechanical energy per unit mass is greater than 0. Negative closed orbits, 0 parabola, greater than 0 hyperbola, right? So if this quantity is positive, that means that this applies. And that's what I'm asking. Is the magnitude of the kinetic energy, which is this quantity, greater than the magnitude of the potential energy, which is this quantity? Yes. True. Done. Now the other angles questions, they are both two singular configurations. If you're doing a 1-2-1 and the second symmetric rotation and the second angle is 0, that is a singular configuration, meaning that the second rotation is doing nothing. You're rotating about the x-axis 10 degrees, and then you're rotating another 10 degrees about the same axis. So it's the same as doing 20 at the beginning and nothing else. So are they the same? Yes, there is no difference. And basically it's the same question for 3-2-1. The difference is that with this asymmetric rotation sequence, the 90 degree on the second rotation is a singularity. So in that case, if first and last rotation, the one on axis 3 and 1, they have a constant difference, you get the same rotation. So that is also equivalent. Doing 10, 90, 10 is the same as doing 20, 90, and 20. Those 10 and 10, 20 and 20 cancel each other, right? Try to see it with a sketch. So yeah, basically there are two singular rotations and there is no difference there. I'm going to save the best for last, of course, this one. Now, if you have done homework 2, you are experts on ground tracks. So 1 and 2 should have been quite clear. If I say geostationary satellite, that means on the equatorial plane. There is no other choice unless you're doing something weird with solar radiation pressure and, you know, exotic orbits that people have been talking about that I haven't seen yet. Yes?
Whenever I put it into the program, it gave me 29 degrees latitude. Is there a reason for that?
29. Latitude.
Yes.
That's Gainesville, right? Or is it? Yeah, I think it's Gainesville.
From the Perigee.
Which program do you use? Your program?
Homework 2, and I got rid of the percent sign for the section for the satellite. And under latitude, I believe it said something about GST.
So we should probably, if you come to office hours, I can look at what you've done on your software. But basically what I'm asking here, the first thing that I'm telling you actually is, I'm already telling you what the longitude and latitude are, right? If you are geostationary, you cannot have a latitude other than 0. If you are on the equatorial plane, that's geostationary. You can't go out of that. Otherwise, there is no geostationary orbit. So the first part, geostationary satellite, means latitude is 0, no matter what. It stays at 0. And then what we do with the geostationary satellite, we put it on top of a longitude, hoping to look down all the time at that longitude. And if you don't have anything else other than Keplerian gravitational force, meaning if your only acceleration is this one, then it's not going to move from that longitude, right? And actually, when I told you a week ahead of time the homework 2 was going to do ground track, I told you, why don't you stick something geostationary in there and see if it actually does stay where it's supposed to stay. What is the longitude by definition of London, Greenwich? It's 0 longitude. So you put a geostationary satellite at 0 longitude, it stays at 0 and 0 all the time. That is the purpose of that satellite. It's looking down at the same spot on the planet. Does it make sense? I've seen many different interpretations of this. I think some, for some reason, believe that had to be on top of Greenwich. That is impossible. Can't have a geostationary satellite on top of a place on this planet that is not on the equatorial line. Doesn't happen. Unless you're thrusting like crazy continuously. And it probably lasts 2 minutes. It's not natural. It's not a natural orbit. It will not stay there, right? You can try. You can try to stick in the Greenwich latitude, which is not 29. 29 is Gainesville. Greenwich is like 40. I mean, Rome is 40 something, 41, I think, and Greenwich is above. It's probably 45. I don't know, or more. That is the answer for that one. Second one, same kind of idea, just to see if you could see things in 3D. So what happens if you have an inclination of 50 degrees? It means that your angular momentum vector is at 50 degrees with a z, right? Okay. Well then, if this is h of your orbit, and this is 50 degrees, that means that the plane of the orbit, I don't know how it's oriented for the other orbital parameters, but it's going to be, you know, also at 50 degrees with respect to the xy plane, right? So you can't see this angle be more than 50. That's such. Try to go back to your homework 1, the International Space Station ground track that you have computed. It's oscillating between minus 51, I believe, and 51 point something degrees, which is, that's the latitude, and that is the inclination that you're given for the ISS, right? You can probably open it and probably run it. Let's see, this was homework 2, right? Yeah, okay, let's see. Yeah, 51 degrees. So if, unless I have modified this program, it should still run and show me, yeah, this plot. Yeah, I mean, you can't pass that inclination, right? Does it make sense? Just think about simply a plane and its normal. They go together, right? So if I move the normal 50 degrees from the z, the plane of the orbit is going to lift up with respect to the equatorial plane 50 degrees. And that is the latitude angle. You're not going to see anything more than 50. Because you're moving in this plane, right? In a circle or an ellipse, whatever it's happening, you're moving on this plane that is lifted 50 degrees from xy. So you're not going to see that angle to be more than 50, ever. Make sense? So you could have run this, actually, just to see what would happen. That was an option. Let's see. OK, the tricky one. Why did I say that I was going to give you less points if you engaged in calculations? Not because I'm mean, because I didn't want you to engage in calculations. I just wanted you to draw the vectors and see what was going on. So, and recognize that velocity. X, y, z, your initial vector is such that the x and the y are the same, right? 10,000 kilometers on x and 10,000 kilometers on y. And so this was R0. And then V0 happens to be exactly at 90 degrees with this because it's only on the z direction. So this is V0. And that expression there, square root of 2, square root of mu over R0 is the escape velocity. It's a parabolic flight. You just have to remember that something had to trigger in your mind, oh, this looks familiar. The square root of mu over r, it's a circle. If you start increasing, you're going away from a circle. So that means your first answer is eccentricity is 1. That is one of the orbital parameters. I don't want a, right? I told you, leave a alone, because that would actually require some calculation. I didn't need that. So that's the first one. Then you need to figure out the other ones. Now, if we're talking about orbital parameters, we need to define the plane of the orbit. Now, these two are 90 degrees. So the plane of the orbit is the plane that contains, for example, R0 and Z, right? R0 and V0. It's this plane that is cutting the XY, that it's a 90 degrees with the XY plane, right? That is going to be the orbital plane. Or if you want to see in a different way, R0 cross with V0 is going to be some vector that is in the xy plane. We see that? Am I losing everyone? Yes?
R0 cross V0 be 0?
I'm sorry, say that again?
Wouldn't R0 cross V0 be 0?
If you have an orbit, oh, so let me ask you this question then. If you have an angular momentum of 0, what kind of trajectory are you following? Oh, it does exist. You're going straight into the planet, or you're flying away straight away from the planet. Velocity and position are at 90 or I'm sorry, at 0 or at 180. It is possible, but it's not really that interesting. Yeah.
I know there's obviously no partial credit on like 9 out of 10 of these questions, but what if you got like 4 of the 5 orbital parameters correct? You get a 0? No. And again, this is just to, my idea with specifying with that sentence there was that I really hope that people would not engage in crazy calculations and just give me a reasonable, quick answer with some justification, of course. But again, if any one of you has different issues, you talk to the TAs first, then you come talk to me. I mean, it depends. I don't know. It depends on what you've done. I've seen people turning in solutions with equations that I have never seen before. Believe me, I've seen, so I probably have to talk to them to understand what happened. So it's a case-by-case scenario. But my idea was, don't do calculations here. Just show me that you recognize what's going on. Yes? R is this way, V is this way. Should be coming. It should be this way, yeah. But anyways, regardless of where it's pointing, I do know, do we agree that it has to be in the xy plane, right? And so that gives me the other orbital parameter, which is the inclination. Because if this is the h vector, this angle is 90 degrees, right? So inclination is 90 degrees. Now, what happens at perigees and apogees of orbits? In this case, you only have perigee because it's a parabola. That is the places, those are the places where this happens.
So this is also the perigee, right? So this is perigee. Nowhere else you have the velocity and r at 90 degrees, except if you are in a circular orbit, which is not the case here, or if you are at apogee or perigee of an ellipse. This is not an ellipse. There's no apogee. I mean, yeah, it's at infinity. So that is the perigee. Well, let's leave it there for now. What is this also? When you're crossing south to north, what do you define? The line of nodes. This is the line of nodes. Here it is. So this is your big omega, Ran. And since this is 10,000, this is 10,000, this is a triangle with the same two, a rectangular triangle with two sides that are identical. This is 45. And now, since that is perigee, it implies that my omega is 0 and my true anomaly is 0. Because my eccentricity vector is actually pointing exactly like R0. Do you see that? No? Yes? So if you don't believe this solution just by looking at the plot, I posted the MATLAB file that actually runs the conversion, takes that vector in, and it gives you those numbers. 90, 45, 0, 0. And I didn't need A, because to do A, you actually had to compute H and find the A of a parabola. So I didn't want you to do that. So I think that's all we had in the test. We'll see how it went. How many feel good about this? No one. Okay. All right. We'll see how it goes. I don't know the average yet. I don't know if they're correcting them. So, do you have any questions on this? Any other questions? So do we agree that homework 2 was really very related to 1, 2, 3 other angles? There was an uncollected homework, but no calculations. These are what is it? It wasn't related? Ground tracks and longitude and latitude are not related to that? Ground track is made of longitude and latitude. You cannot say that that is not related to the equation. Okay.
Because the homework is all entirely in MATLAB, where this is kind of like more conceptual problem.
How can you write down your own code if you don't understand the concept that it's behind the lines of code? Unless you're copying it from someone else's code, then you must know what's behind the code. I think I've repeated this several times. You need to sit down and do it yourself. It doesn't matter if you're copying it from the board because I projected it, or you should not really cooperate with anyone else, actually. But, at the end of the day, if you have code that runs and creates a plot, and you have no idea where that came from, that is not your work. You understood nothing at all. So if you don't know how to create a ground track, what that means, it doesn't matter if you're running that code and it's plotting that line the same way I have it. So you really should do it by yourself. That is the idea. Because if you don't know how to do arc sines and arc cosines of which of the components of the R vector and how to correct and what are the angles that you need to plot, then how can you do homework 2? That's my feeling, at least. But we'll see how it goes. Again, if I have an average of 40, then it's a concern. If I have an average of 80, then it's probably not that big of a concern. Yes?
So for question 1, it's definitely going to be all or nothing. You can't get half credit if you got working.
So if you give me a latitude which is not 0, you don't know what a geostationary satellite is. It's the end of the story. I mean, I can't just send you to the next, to your employer that asks you something about geostationary satellite and you tell that the latitude is 29. I don't think it will look that great. You really need to know what that means. Yes? Okay, longitude. Oh, why did you put 29? You did put 29. You choose to have 29 then.
Because when I put it into the code, I can pull it up.
Yeah, I have to look it up. Yeah, I have to look it up. Because 29 is, I think it was it had to do with Gainesville, right? Yeah. But it was the latitude of Gainesville. Longitude of 29 is somewhere in Russia, probably. I think so. Anyways, All right, guys, don't sweat it. Again, I try to adjust to how you have done, but again, if 90% of the class got it right, that means it was making sense. If not, then I am the one who's not making sense, but I think this was related to what we have done so far. And again, with 50 minutes, I don't want people to go into crazy calculations because the thinking behind the calculations is what matters. Calculations anyone can do. You can learn a piece of software today, use it for 2 months, and then you're done for 2 months and you forget about it. You still need to be able to think. Yes?
The code says gave the RAM and GST times 5.
I really have to look at it. I'm sorry, I don't know. Yeah, we can see that. I have office hours after this. All right, so if you don't have any other questions other than specific things that you have done. Yes?
I want to understand number 5. You say they cancel each other.
Oh, yeah, 3, 2, what is it, 3 to 1?
Yeah, I don't understand how it goes.
Yeah, I got opposite. I got
3 to 1. So, rigid body, oh man, if I have a mistake, I'll fix it. But 3 to 1, I've done this before, right? See if I can get hooked up on this again. 1, 2, and 3, right? What are we doing? 3, 10 degrees. 2, 90. X, 10 degrees. It's pointing this way at you, right? Now, if I do a little more, 20, 90, but then that 20 is on the new x-axis is going to cancel with that initial. Yeah, I know.
I caught up with it, you know, that being like a singularity.
I'm sorry. Guys, I
caught up with the 90 being like a singularity, and like how we're not supposed to do that.
Yeah, you're not supposed to do that, but that because
Like a whole couple.
what did we say? We said that singularity is a problem. It's not that it's impossible to see this happening. It's just that you are representing this final orientation with infinite combinations, because the first and last angle, as long as they are the same number, they cancel each other.
I kind of thought that's what you're looking for some reason.
Yeah, it doesn't matter that you cannot. The sequences that we call Euler angles, it's 3 numbers that I choose to use to basically tell you this is how this object is oriented. Its 0 reference orientation would be like this, because that's the x, y, and z of this room. But it's actually like this, and you tell me what you want to use to represent it. If you use a 3 to 1, and the 3 to 1 is like that, it's a bad idea. You want to use something else. It doesn't change the fact that this object is pointing like this. It's oriented with the face towards you. Yep. Again, I'm really surprised that you guys have seen Euler angles for the first time in this class. If you have done dynamics, even at the undergraduate level, I think you should see Euler angles. You skip that section? That's a bad idea. Anyways, we covered those, right? All right, so I think it's time to move on. Again, I don't have too much energy today, so I'm going to start a little bit and pick it up on Friday. But it's time to talk about orbital perturbations. Perturbations. Okay, so this is what we have done so far, except you have the code for J2, but we don't know what that means yet. But this is what we've had. This is the force that is acting on the unit mass that you call spacecraft around the planet. If this is the mu of the planet Earth, is G, is the universal constant G times the mass of the Earth. And that's what we have used for Keplerian orbits, right? Well, in reality, there is something else here. There are perturbations, there are other types of accelerations that affect your motion. So no orbit remains in the same plane with the same constant orbital parameters at all times. Now, there is a lot of different perturbations you can have. We kind of started talking about one type. What is it? If you maneuver, you're perturbing the orbit, right? That is the first one. We've done impulsive maneuvers. I hope you're doing the uncollected homework 6, whatever that is. Yeah. That would be continuous, but thrust in general, so whatever you create, it's a perturbation, a desired one. But then drag, atmospheric drag, if you are below, say the LEO is defined up to 1,000 kilometers, we really don't have much atmosphere after 700 or so, but that is usually the threshold for all the atmospheric models that exist. So let's say that this is valid below 1,000 kilometers, but it's actually a little less than that. Okay? So this is only in LEO, of course. If you go above LEO, that doesn't affect the spacecraft anymore. But there's other things. There could be solar radiation pressure. Again, if you have big surfaces and they are pretty reflective, you do get, over time, perturbations. You do get a small acceleration that is continuously there and leads you away from a nominal Keplerian orbit. And then the one that you have used to run and will demonstrate in very few lectures is it's basically the shape of the planet. And we'll stop at what we call oblateness, meaning the fact that it's not a sphere, it's an ellipsoid. I think that pretty much covers, well, there's something else actually. It's a good thing that I have a list. It's pretty important actually. What causes the tides? The moon. The moon is, believe it or not, moon and the sun, especially when you go to higher altitudes, geostationary satellites, they do affect your motion. Geostationary satellites stay in the equatorial plane if you only have this. If everything is perfect, that is fine, they stay there. One of the effects of the moon and the sun is that they drag you away from the equatorial plane and you start oscillating in the Z. And that's why every couple of weeks or so they have to thrust and correct, because you're not going to stay there in reality. It will take a while to drag you away, but so all these things are perturbations. They can be perturbations or they can be something that helps you. So in my research, if we have time towards the end, I may show you what we do with differential drag in low Earth orbits. You can use drag to maneuver the satellites with respect to each other. The OrbCom constellation, I think that's the name, I don't know if they still do it. There are satellites separated several kilometers from each other, and they rotate solar panels every once in a while to correct their separation using variations on the drag force. So they create more or less drag so that they can remain at the same distance. So perturbations can be exploited if you have the means to do so. As I said, Patrick is working on this. People are looking at solar sails to obtain thrust without any propellant. So it is a perturbation, but it can be a control force. The Sun-Synchronous Orbits, they exploit the effect of oblateness of the planet so that your plane of the orbit is looking at the sun all the time in certain inclinations. Not aware of any use of moon and sun, but I'm sure there is one. But anyways, they can see as a bad thing or something you can use, okay? Yes? Collision, yeah, collision is a perturbation, yes. Yeah. A laser making you explode as well, but yeah. Micrometeorites, they can be. Actually, I don't think it's listed as one, but, and I don't know what is the percentage of impacts that you get depending on the altitude, but they may affect your trajectory, I guess. I'm not aware of studies about that. They can mostly damage, your spacecraft, but if they're small, they may not affect your trajectory. But yeah, they do happen. Okay, so just to give you an idea, I have some numbers here. At this altitude, at about 1,000 kilometers, so if we use J2, which again, for now, we'll call J2 what has to do with the oblateness at the poles, and then we'll have an actual explanation of that formula. So this is going to be 10 to the minus 2 times A0. So if I call A0 this quantity, mu over r squared, which is the norm of the acceleration, the the regular Keplerian acceleration. So if that's the attraction of the planet that you would have with perfect conditions, well, J2 is 100 times less than this quantity at 1,000 kilometers, which may seem very small, but over time does make a difference. Then the moon and the sun, they are a lot less, 10 to the minus 7 there. But they go up with altitude. So this is the edge of low Earth orbit. As you go higher, they do increase. And you get to a point where the attraction of the planet and the moon, for example, they kind of balance each other. The Lagrangian points, if we have time, we'll talk about them. The future telescope from NASA, James Webb, is going to be, I think, on the Lagrangian point on the other side of the moon. It's going to replace Hubble. So as you go closer to the moon, of course, it starts becoming more and more important. And then solar radiation pressure, just to give you another idea, at that altitude is 10 to the minus 9 A0. So it's much, much smaller. Okay. So how do you address these perturbations? What do you do? Well, the obvious thing to do is to give a model for them, write some expression for what they are. We're going to start with drag. And see if you have analytical solutions in some cases, or just use numerical integration as usual. So if you have done a collected homework 6, you have basically done already kind of perturbations. You have added continuous accelerations in certain directions. And what you are plotting as you integrate numerically the equations of motion in terms of orbital parameters are the, I can erase these, what are called the osculating orbital elements. In other words, you have some perturbation that it's acting on your spacecraft, and you have an equation for that. You put it in your equations of motion. For example, here I have J2 plus the drag, if we get to discuss that. And at each time, you get a position vector of t and a velocity of t, right? Two vectors in MATLAB, for example. At each given time, you have a position and a velocity. And you do know that you can convert this into, say, major axis, eccentricity, inclination, RAN, argument of Perigee, true anomaly, with the functions that at this point you have. Now, if you have perturbations, this is not going to describe, as position and velocity evolve in time, are not going to describe an ideal elliptical orbit that repeats itself, right? It's going to describe a different type of trajectory. And so these, in particular, these 5 that would remain constant if you only have Keplerian acceleration, they will change. So at each time step, you have position velocity, you extract the orbital parameters, are not going to be constant anymore. At each time step, you have a set of orbital, so forget about theta because it's basically the time on your orbit. But these 5, again, they remain constant if you don't have anything else other than r double dot minus mu over r cubed r, right? Well, now they're not constant anymore. They are changing as the position and velocity evolve. And so what you are doing by converting at each time step, for example, the state vector into orbital parameters, you're computing what we call osculating orbital elements. So at that particular instant in time, you get the orbital elements that would correspond to a Keplerian orbit if all of a sudden you switch off the perturbation. Right? So I give you r and v, at a given time you compute the orbital parameters. These will remain the same if you don't have the perturbation. But the perturbation is there, so you're going to integrate another time step. You have another r and v that correspond to something different. Even the ground track problem, you plotted the orbital parameters, right? So I do think that they were not staying constant, right? They would change probably not that much. It's only 15 hours, but they don't stay constant. Let's see. Yeah, argument of Perigee is changing. The RAN is slowly going down in this case. See, it's not staying constant because there is J2. I am modeling somehow the fact that the planet is not a sphere. See, the inclination is kind of oscillating. Very little, but it's oscillating. So the orbital plane is doing this. It goes back and forth. The eccentricity is staying pretty slow, it's pretty small, but it's changing. same major axis is changing. It's actually changing how many kilometers? 12 kilometers up and down. And this is due to J2. Remove J2, you will see that that is not the case anymore, except numerical errors in MATLAB, of course. But so if you go in 3D, this line doesn't look like a line anymore, right? The line doesn't overlap on itself anymore because you have perturbations. But osculating means that at each particular instant in time, you have the orbital elements that you would have if you all of a sudden remove that perturbation and you let it go with perfect Keplerian conditions. Make sense? So that is one way of looking at perturbations, basically measuring what are the effects that they have on orbital parameters. And we're going to get very quickly to that point of actually writing differential equations for this, an A dot, E dot, I dot, omega dot, little omega dot, that have to do with the type of perturbation. This word comes from Latin, and it means kiss, has to do with kissing, because the orbits, the real orbit and the osculating one, that's exactly what they do. They kiss each other at that time. They are osculating each other. It means that if this is your planet, this is your r at a certain time of t, and this is your velocity at a certain time of t, and you solve for the orbit that you would have in perfect Keplerian conditions. Say that you get I don't know, some ellipse like this, right? Well, this is the osculating orbit of something that probably its tangent here is at the same position as the same velocity, but reality is, I don't know, something like this that spirals out, right? Maybe because you're thrusting with the velocity, that's your perturbation, you have something else going on. Or you add drag, and so this is, instead of going out, it's going in. It's spiraling in until you burn into the atmosphere. So, but these orbit here, if I can make it a little thicker, it would be the osculating one. Doesn't make any difference. It's not working. Yeah. Is this the right one? Yeah. This would be the osculating orbit at that particular time. So as you move on another time, then the osculating orbit will be something else. So it's just you freezing time and looking at the orbital parameters right there, and see how they evolve. Yes?
What is J2 doing?
What J2 is doing is just basically taking that sphere there. We know that it's not a sphere. The poles are a little closer than 2 points at the equator, so you take the sphere and you squeeze it. So J2, the acceleration formula I gave you, and will demonstrate, is taking into account how gravity is changing around the planet because of not being a sphere anymore.
Okay, so, but like
At the end of the day, J2 is changing exactly what you've done. One of the what we're seeing here. Oh, I closed the plots. The main effect is precession of the line of nodes is changing the REN. It is making the other ones oscillate mostly. So there isn't any. So there are two types of perturbations effects on orbital parameters. We call them the secular ones. Would be those that have a continuous drift, and that is what the REN is doing. REN is constantly going into. So this is, as you can see, it's going up and down. It's oscillating, right? The REN, there is some oscillation, but it's steadily going down. So that's a secular effect. That's how it's called. So the main effect of J2 is really this one, is changing your orbital plane. The other ones are changing, but they go back and forth between two extreme values most of the time. And so the effect, I mean, you can run this for longer. I don't want to do it here because it will take forever. But this, I mean, maybe I can. Let's try. See if it doesn't crash. 15 hours, I want to do, let's do 5 days. See if this works. That line, the red line, which is your orbit, is going to cover a lot more 3D space. Yeah, this is going to take a while. While it does that, let's start talking about drag. It may crash. If it does, I'll have to debug the code. Yeah, and it's a lot. Yeah, that's what happens when you have things that change a lot over time. What did I run, by the way? Did I run Homework 2? Yeah, I did. Okay. Yeah, it wasn't a good idea. Well, this is steadily going down. and that makes sense. The other one are oscillating, and they look pretty ugly. But this is what I wanted to show you, is that the trajectory, as you can see, is not, you know, a line anymore. It's a line that is lying on different planes over time. The plane is changing. And the oscillation of the other parameters, you can't really see it that much. I can kind of see the change of the RAN, which is, again, the intersection is the angle given by the intersection, well, the line of nodes and the x-axis. That is clearly changing. The plane containing the orbit is changing. Yes?
So it's going to continually go down.
It's going to go around.
So it just gets way out of line.
Yeah. That's why you have to correct for those things. Okay, you have to trust every once in a while. That is one of the things you have to correct for. And the other one, if we introduce drag, as I was going to do, is that you have to regain altitude every once in a while. So drag, I want to open this other image here that is not going to open. What we do with drag is, well, only 5 minutes. Well, I just say that it is modeled more or less the same way you would do with an airplane in terms of the formula that we use. It's 1 over 2. Let's see. So we are at chapter 12. I'm just skipping a few, and then we'll go back. Okay, this is just to give you an idea of what happens. Okay, so 1,000 kilometers altitude. We just say there is no more atmosphere, but even at this point, there's really much else other than just space. The norm is, we say 100 kilometers is when space begins. This was the first spacecraft, first as artificial satellite from the Russians. He had a Perigee of 230 kilometers or so. I think it lasted, I have it here, a few days. Not long. 3 months. Yeah. Lasted 3 months. The Perigee was pretty low, 200-something kilometers. There is atmosphere, enough to bring you down every time you come through Perigee, which is high speed, because it's Perigee, is the highest on your orbit, and the highest density, because you're the closest to the planet. So that is taking away a lot of energy, so it came down pretty quickly. Then the US launched the Explorer-1, which is a very interesting spacecraft. At Kennedy Space Center, there is a museum as you get in on the left, and there are a lot of interesting things shown there, and one is a model of Explorer-1. We discovered, actually, a lot of things with Explorer-1 about the attitude dynamics of rigid bodies. So you may want to go there and check it out. This lasted a lot more, 18 years. See, just a few 100 kilometers of difference, a lot less atmosphere, stayed up by itself. These were not maneuvered. They were not thrusting or regaining altitude. It just came down slowly. The ISS is at about 400 kilometers altitude. And I'm not sure how often they thrust. It's pretty often, 2 weeks or so. I'm not 100% sure. But you do lose altitude, especially because it's big. So the crosswind surface area is big. The model that we are going to use, and I'm just writing it here, we'll spend more words on this. 1 over 2 density of the atmosphere, crosswind surface area, the ballistic coefficient over the mass. This is the acceleration due to drag. The norm, right? No signs here. V squared. And this is the velocity relative to the atmosphere. We'll comment on these things. But the bottom line is that the more density you have, the more surface you have, the more CD you have in velocity, the more you go down, because that acceleration goes up. Hubble, it's higher, still LEO, still affected by drag. Last time it was boosted, as far as I know, it was with a push from the space shuttle, I believe. But it will go down by 2025 or something like that if they don't do anything else. It will come down eventually. So drag is the very first one with J2 that we must be aware of, because it does affect the beginning of space. As we go above 100 kilometers, we do have drag. And even if you want to go higher, you have to deal with it until you reach 1,000 kilometers. And I think for today we can stop, because it's 50. We'll continue next time.